In this lesson, we're going to take a look at how we can predict what the images formed by a curved or spherical mirror are going to be. Now, we need to discuss a little bit of vocab and what I mean by a spherical mirror. And we looked at curved mirrors in labs, and those were sections of a whole circle in 1 or 2 dimensions or a sphere in 3 dimensions. And so a spherical mirror, we assume, is a small section of a larger sphere. And when light hits that, we have what's called the principal axis, which goes from the center of the mirror and passes through its radius of curvature, which I'm going to go ahead and I'm going to label that point C. This is a spherical mirror. And when light rays hit it, parallel incoming rays, they are going to bounce off, follow the law of reflection, so my normal would be here, and it comes out through here. Now, for a spherical mirror that's fairly large compared to its radius of curvature, all of these light rays that are going to focus are not going to focus to the same point. But for a small section of a spherical mirror, they essentially do. We can assume that they do. So if I draw this line from the center to the mirror, that is actually perpendicular to the surface there. That's actually the normal. And so that makes this angle right here equal to this angle right here. That's the law of reflection. And then that's equal to this angle right here because these are parallel lines cut by a transversal. And so that makes this an isosceles triangle. So these two distances right here, where the reflected ray hits that principal axis and between the center of curvature and where that reflected ray hits, those are equal. And if I did that for a different parallel ray, say closer, that ray comes in, and again, if we draw in our radius of curvature, then this light ray reflects through there as well. And so this is equal to that, and we can keep progressing that closer and closer. And what we see is this spot right there where the reflected rays focus for a small section of a spherical mirror is going to be halfway between the radius of curvature and the edge of that mirror. And so what we've just looked at is where these rays focus or come to a point. We call that the focal point, and we have the focal distance. So the focal distance is equal to the radius divided by 2, or half the radius. So we take the whole radius of curvature divided by 2. That's where the light rays will focus for a spherical mirror. Now, that is a helpful point to know because that's where parallel light rays from a great distance will come in and focus to. So if we were trying to look at an image of the sun, we could have the sun's rays come into this curved mirror, and then we would put a screen right here at the focal point, and we would see the image of the sun produced right there. But if the object that we're trying to look at in the mirror is far away, or not far away, then say closer to the mirror, where is that image going to be and what is it going to look like? Now, you did have an opportunity to look in some curved mirrors, and you know that depending on if it's concave or convex can produce different images, and depending on how close or how far you are from that mirror, you can get different images. So the way we figure out what our images are going to be are by using these helpful tools, ray diagrams. And a ray diagram always uses 3 rays. So I'm going to draw my mirror and my principal axis, and I'm going to label my 2 points. I'm going to label my radius of curvature, and I'm going to label my focal point. Now I'm going to put my object, and I'm going to use an arrow pointing up. I'm going to put my object right here between the radius of curvature and the focal point. And I'm going to draw 3 rays. The first ray I'm going to draw is from the tip of this object, parallel to the principal axis, and then see what it does. Well, since that's going to go through the focal point, I'm going to draw that reflected ray back through the focal point. And I'm just going to keep drawing it, right? So that's my first ray. So it was from object, parallel to axis, and so by the law of reflection, it reflects through the focal point. Okay? Now the second line I'm going to draw is sort of the opposite of that one. Instead of parallel and through the focal point, I'm going to go through the focal point, and that light ray will reflect out parallel to the axis. So there's my reflected ray. So second, from object to the focal point, and I'm going to use FP for that, and then it reflects parallel. Now, that's actually enough to figure out where this image is going to form, if I extend my principal axis back, of course, every point on this is going to follow this similar pattern, but since the bottom of this arrow is on the principal axis, that's not ever going to change. I know the tip of my arrow is going to be right there. But there is a third ray we can use to check, and that one goes through the radius of curvature up towards the mirror. My mirror was not tall enough. And then it's going to bounce straight back, since that's actually already perpendicular to the surface of the mirror, and I did a bad job on that. But that one comes straight back, and if I had done a better job drawing this, oh, no, I missed. So that comes through there. Those three rays will line up and converge at one point right here. And since that came from the top of my arrow over here, that's the top of my arrow over here. You'll notice it's taller than this arrow. It got magnified, it's bigger, but it's also inverted, right? So I can put my object anywhere on here, and I can figure out, using this ray diagram and my three rays, where the image is going to be. So remember, my third ray was just through center of curvature. Okay? And we use 3 to make sure we're doing a decent job with our picture. Now, what happens if I move my object around, or I switch from a concave mirror to a convex mirror? What we have to think about on that is the idea that just because the light rays are diverging does not mean it doesn't look like they didn't come from a single point. And so let's go ahead and use a convex mirror. Convex mirror also has a radius of curvature and a principal axis. So I'm going to put my mirror here, and I'm going to draw my principal axis through here. Wow, that was bad. I'm going to put my radius of curvature, and I'm going to put my focal point, and now I'm going to put my object right here. Okay? And I'm going to use the same three rays from the object parallel to the axis. So from my object straight parallel to the axis to the mirror. Now it says reflects through the focal point, but it can't because the focal point's back here. So it's going to reflect as if it had come from the focal point. So now it reflects that way. Right? The second one, it says from the object through the focal point. Well, I can't go through the focal point, but I can go towards the focal point. So I'm going to do that. Okay, if that line had continued, it'd be right here, and it reflects straight back parallel to the axis. And then my third one, and I'm going to go ahead and get rid of that dashed line. My third ray would be straight towards the radius of curvature, and it would come straight out. And so that's headed towards my radius of curvature this way. Now, and that reflects straight back this way. These 3 light rays can be picked up by the eye, and they're diverging as though they had come from some point straight back here. So I'm going to follow this line straight back, dashed in, and this line straight back, dashed in, and right here is my image. And it's a virtual image because there aren't any light rays back there, but I followed the same basic light ray rules. I use those same 3 rays, and I can figure out where my image is. And you'll notice it's shorter, right? And we know a convex mirror produces an upright virtual reduced image. We saw that when we were looking at these mirrors in the lab.